Hello, welcome to Computer Graphics Rendering. In this video, we're going to talk about shadows. In particular, we would like to talk about the use of shadows in computer graphics, ray tracing, shadow volumes, shadow mapping, and finally, in a subtle effect called ambient occlusion. So, when we talk about shadows in computer graphics, the situation that we're looking at is we might have an environment, which I'll use this to represent a wall inside of a room, and we have lights. And in this particular scene, obviously nothing would be in shadow, the wall is lit, and we can use our normal reflectance functions to determine how much of the wall is lit and how much light is going to be reflected off of it. So if we add an object, say a ball, then we would like to be able to determine from the viewpoint of a camera how much of that wall is in shadow. And so we might say that the ball is a shadow caster and the wall is a shadow receiver. Sometimes, depending on the 3D program or the software you're using to develop a program, you can identify some objects to be casters and some kinds to be receivers, and this can help optimize the quality that you can get in your final images that you produce. So there's a few ways that we could approach the shadow problem, and it all depends on whether we're approaching it from a real-time rendering perspective or just the typical high-quality path trace renderers. So let's quickly just talk about the path tracing method, ray tracing method, and the approach to determining shadows. So in the ray tracing approach, we've talked about in previous videos that you can use shadow rays. And what shadow rays allow us to do is, as we're tracing a ray from the camera, we can, perhaps there's a light out here that will light up the back wall, and as we determine we can shoot a shadow ray to each of the light sources and determine if something is occluding it, in which case there's an occlusion here but there's no occlusion over here. And what this means is that this light, we'll call this light 2 and we'll call this light 1. That light 2 will cause the surface to be illuminated on this back wall. However, because there's an object blocking the path from our point X that we would like to shade, we would say that shadow ray failed. And so if there was no light 2, then that area would be shadowed. Okay? Now, if we were then trying to decide, if we were doing path tracing, do several bounces, then we might cast a shadow ray from this new surface, maybe we'll call this Y, and we can tell right off the bat that there is no path to light source 2 and no path to light source 1 from this part of the object. And so if we were only doing one bounce of light, then effectively the box area here is in shadow, it's not reflecting any light, and therefore there's no additional illumination. Now if there had been another light source, say over here, and that we will call L3, and we had cast a shadow ray, then we could then backpropagate that reflectance back to X, and then we would have some indirect lighting that affects our point X. So ray tracing and path tracing in general have a very flexible way of allowing the final renderer to accumulate shadows, and it's the best way if you want to get the perfect soft shadows is to use path tracing or ray tracing to do that. If you only use one bounce of light effectively, then you'll get very hard shadows, and if you're trying to get soft shadows, then you would have to do something extra. For example, you could change the width of the light, so that instead of point lights you have, or even directional lights, that you would then sample off the entire surface of the light, which of course is going to increase your rendering times, but If you do that, then areas over here, for example, let's say we're trying to shadow this area and shadow this area, you'll see that in here is going to be a spread of where you have the most intensity in the middle, and it'll fall off towards the edges. Okay, so let's go ahead and take a look at the next method, which is a real-time method called shadow volumes. So this next method is called shadow volumes, and it was invented by Frank Crow in 1977. And the way that this particular approach works is, for one, we're doing real-time rendering, so instead of tracing rays, we're drawing polygons on the screen. And so if you have an object that is going to cast a shadow in a scene, essentially what we would like to do is first let's draw the scene as if it was completely in shadow, and then let's try and figure out what parts of the visible scene are then not in shadow. Okay, and then we render the scene again, and we just shade in the parts that we have determined are not shadowed. So we use a tool called the stencil buffer, and we combine this with the depth buffer to do this particular method. So one of the first part is that you have to determine what the volume is for the shadow. So let's just quickly pretend that the cube here is the shadow caster. So in order to do this particular method, we have to create these volumes that we can then render a mask inside the stencil buffer. So one of the ways we do this is, first of all, we're going to render the front-facing and the back-facing parts of the shadow volume separate. So front-facing, in this case, this is front-facing, and this one, because it points away from the camera, is back-facing. And the goal that we're going to work here is that if we render the front surfaces and back surfaces, then we can count the number of times we see a front-facing and count the number of times we see a back-facing. In other words, we're going to see when the light enters the shadow volume and when it leaves the shadow volume. And if then the surface you're trying to shade is then we have an odd number, in other words, we haven't come out, then we know that that area is being shadowed. So the way that we generate this mask in the stencil buffer is that we're going to disable writes to the depth and color buffers, and we're going to use backface culling. In other words, we don't draw these parts, and we're going to set the stencil to increment. So I'm going to put S for stencil. So we're going to increment. We're going to cull backfaces. All right, and then we're going to render the shadow volumes. So in other words, only the front-facing ones are generated. So these get rendered the first time, and after that, then we use front face culling. In other words, instead of drawing the front faces, then we draw the back faces. So now we're going to cull the front faces, and then we're going to set the stencil operation to decrement. So now the stencil, we call it to go down. And then we render the shadow volumes again, and now this time only the back faces get rendered. And so after all of this is accomplished, essentially anything that's lit will have a 0. So this would represent 0 in the stencil buffer, and this would represent 1 because we're inside, we're inside, we're inside. Now we're out. So as we're drawing, we basically get a mask now that from the viewpoint of the camera, we can see what is visible and what is not. Now, the only time you might have this becomes problematic is then if we have the camera inside of a shadow volume, in which case, because the front facing has not incremented, then technically we get zeros here because we have not seen a front face. So there are some algorithms that you can do in order to solve this particular problem, but we just want to be familiar with the general idea here. So let's go ahead and take a look at the next method of shadows in real-time graphics called shadow maps. So the process of shadow mapping was invented by Lance Williams in 1978, and this is the most used algorithm to generate shadows in real-time rendering today. So let's bring back our scene, something similar from the last slide, and talk about how it works. So just as the shadow volume was a multi-pass method, the shadow mapping algorithm has also got several passes, and the main pass, the first pass, is to render the shadow maps. And a shadow map is essentially nothing more than just a Z buffer rendered from the viewpoint of the camera. So in this particular scene, if we were rendering a light map, we might render a Z buffer, and essentially we might, anything visible inside the Z buffer would then get rendered to this depth map. So essentially we're recording how far away is every object visible to the light source from the light. Okay, and then the second pass is then to use the shadow map by calculating from the viewpoint of the light where each, essentially what pixel inside the shadow map would have been generated. So from the camera, let's say we're interested in this point over here. So what we want to do is figure out, well, where in the light, probably that pixel right there, would this fragment have been generated? And then we check to see the Z value. So we can tell from this graphic that this Z value would be nearer than this Z value here. So we'll call this maybe Z2 and ZL. This is from the light map. And so we can see that Z2 is greater than our Z from the light map. And therefore we can say, well, that element is in shadow. However, if we had taken a look at ZL instead from the viewpoint of the camera, we would then compare what pixel was stored, and we can say that the object is nearer, or it's the same distance. Okay, so we'll say that so we have the same distance, so this is lit as well. And let's just say we have another object in our scene. Perhaps we'll put that object over here. And let's just hypothetically say that this is a shadow receiver rather than a caster, so it didn't get drawn in the light map. But we'd like to see if it is being shadowed. So we would then look at maybe this point on the object, and well, maybe not this point because it's not in the cone. Let me just erase that real quick. Let's put this object here, and then we'll look. We're interested in this point, okay, and maybe this Z value was the one stored inside the Z buffer, okay, and we'll call that Z3, and we'll call this Z4. So in this case, because the value Z3 is stored in the light buffer, Z4 is less than Z3. And because it's less than Z3, we can determine that that object is not shadowed by the light source. So then we would say, okay, we can go ahead and use our lit shader, or part of our shader, to then render what the reflection ought to be based on that light. Now there are some problems that can creep up with Z buffers, with shadow maps, and that is when the light map and the object are not, perpendicular to each other. So let's see what that looks like. So let me just erase this real quick. And the idea here is that the depth buffer typically has limited resolution. So you're dealing with numerical accuracy issues. So here's your light source. Let's just say this is what's visible, and we have an object here that is at an angle. And so then the case is, well, what about the Z values? Okay, so maybe the Z values jump up over here, and well, let me just redraw that slightly. Maybe in the Z buffer we get this pattern that shows up, kind of a coarse representation of the box, but this is a situation that happens all the time. And so what ends up happening is that if we're trying to determine if this is in shadow, technically it's all lit. So we'll have this part is lit, this part's in shadow, and this part is in shadow, and this part is lit, and this part is then in shadow, when obviously the whole surface should be lit. So one technique to get around this is to add a small offset. And instead of, so when we write values into the Z buffer, then it effectively, if we add the right amount of offset, then now when we do our comparisons, then the whole object is lit from side to side. So what this is called is surface acne. This is a very common artifact that comes up with shadow mapping, and essentially what you have to do with shadow maps is optimize this bias. So we basically add a bias to the or an offset, that's another word for it, to our Z values that we write. That way when we do our comparison later, we can avoid those numerical issues. And part of that is that the scene will have objects that essentially will need to have, if you set the bias too high, then it can cause self-shadowing to stop because it moves the shadows back. So you have to optimize essentially these offsets according to what's going to provide the best quality. There are some other approaches too, though, and that has to do with the fact that when you're rendering a perspective map, which you're often doing, so a perspective is different than an orthographic projection. And so if you can use an orthographic projection, which I'll just put orthographic over here, this can get rid of some perspective aliasing that can occur. And perspective occurs when the object's far away. You get a distortion that happens, and so the shadows actually are not correct. So you might use orthographic for directional lights. But another technique you try is called cascaded shadow maps. And with cascaded shadow maps, essentially what you do is you take your scene and you divide it. So let's erase this real quick. You'll divide your scene in such a way that you construct several shadow maps to help get rid of this perspective distortion. And if your scene is in over here, then use this shadow map. If your scene is over here, use this shadow map. And if your scene is over here, then use this shadow map. And this helps reduce the problem of perspective inside the shadow map. So if you can use an orthographic projection, then that helps. That's good for directional lights. If you have point lights, then you have to use perspective, and so those ones you may need to use CSM if the scene is very large. If this is a small local light source, then it doesn't really matter that much. And then lastly, you may have the case of, well, what if you use different size resolutions for different kinds of objects? So one technique you could try to help improve quality is, render your large shadow maps for your main character, because that's what your eye is drawn to the most. Okay, and to put this in perspective, if you draw a low resolution, like say 64 by 64, you're talking about 4,096 pixels inside the shadow map. But if you were to render a much larger shadow map of say 2048 by 2048, then you're talking over 4 million pixels, which is a considerable amount. So you have to shadow maps that a lot of the GPU hardware can support it pretty easily, but you have to make decisions about, well, where do I use my high resolution maps, where do I use low resolution maps, where does it matter, and then look for ways to optimize quality with different algorithms. So this is essentially how the shadow mapping algorithm works and some of the considerations you have to make. So sometimes shadows are very soft and it's hard to notice them. And so there's a technique called ambient occlusion, which means that if you have a room, typically the whole area is not perfectly lit, and if you were to do something in the corners, you might have some shadows, some subtle shadowing happening in the corners, where the light doesn't really have as good of an opportunity to get to. Okay, and to some degree around the creases, you might have just some subtle shadowing, and part of that, like I said, is the light just doesn't have as much opportunity to get in there and bounce around as compared to, say, the main flat surfaces. Okay, so this technique called ambient occlusion essentially is what we'd like to determine if we have some kind of crevice here. What's the probability that light can get out? Okay, so one way would be, well, let's just shoot a bunch of rays and just kind of see in what directions is it able to even get out, and then determine approximately what percent of the time do they leave and what percent of the time do they just end up colliding inside. Okay, and so you can normally determine a value, we'll call it A for the ambient, right? And that just goes from 0 to 1 on how much shadow normally occurs in this one. And so because in many lighting calculations you have the total output, so the color out equals some amount of diffuse times your n dot L plus some kind of specular light times, we'll just say n dot V to an exponent just to represent some kind of shining lighting. And then sometimes you add a ambient term, which brings up everything from black to some minimum level. But this can look unrealistic, and so if you use this A value here for the ambient light term, then what you can do is for areas that are in shadow, you can kind of adjust how much ambient light essentially is coming off of those areas. So we would expect very little ambient light to come out of these cracks, and we would expect the maximum amount of ambient light to be reflected off these surfaces. So this is a way of maybe approximating that global illumination look that you get with path tracing that you normally can't get with shadow maps or shadow volumes for real-time rendering context. So just by way of review, we talked about shadows in computer graphics, the use of ray tracing or path tracing to generate the highest quality shadows, shadow volumes, and shadow mapping in real-time graphics, and a technique called ambient occlusion that can kind of get us that soft shadowing look that you get in ray tracing, but in real-time graphics. So thank you for watching, and adios.